Okay, hello everyone and welcome to lecture 7 of the Building Planets series. This one comparing the rocky planets in our solar system. Recall what we talked about last time in lecture 6 was about the small bodies in our solar system now. Our solar system is drenched, just to do a little recap, drenched with small worlds, literally millions of them. The large populations are clustered in the stable regions, the asteroid belt, the Kuiper belt, and the Oort cloud, as shown in this kind of exploded diagram. But they orbit throughout the planets as well, small bodies do, including some special cases like the Trojans that share Jupiter's orbit. And now the most distant objects we can detect in the main outside of the Kuiper belt, even outside of past the main Kuiper belt, indicate the presence of another planet in our solar system. So stay tuned. There could be a 9th planet discovered sometime in our lifetime. All right, so this is a huge and fascinating topic that we'll just be able to brush over on today, comparing the rocky planets in the inner solar system. We'll talk about the atmospheres of the planets, some of their surface features that are similar and other surface features that are unique to each planet. And along the way, these ideas will point to processes that happened long ago. And so these processes that happened long ago sometimes sent planets on divergent evolutionary paths. And so we'll be referring to early solar system times as we talk about the planets that we're looking at today. So let's start with atmospheres. First of all, what do I mean by rocky planets? I mean planets that have metal cores, iron, nickel, metal cores, and rocky exteriors, like Mercury on the left, Venus, Earth, and Mars, here pictured in order from left to right, and also to scale. And I'll bring in our moon too from time to time. I'm not going to talk about interior structures, which vary a bit, how big the metal core is, whether the core is molten, whether they have a magnetic field, that kind of thing, even though that's really a little bit closer to my own specialty. Today, we're going to be focusing on the outsides. So first, let's look at the surface temperatures of these bodies. Here's a graph about the range of surface temperatures on each body. But the temperature on the vertical axis is given in Fahrenheit, because most of us here sadly are a little bit more familiar with Fahrenheit. The lines across the graph are the freezing points for water, for carbon dioxide, for methane, and for nitrogen. The rocky planets that are the topics of this lecture are in the yellow box. But I've included some small bodies and outer solar system moons that trail off to the right. Note that a couple of those outer solar system bodies actually have temperatures that rise above the melting point of water, Ceres and Io in particular. They can occasionally have liquid water on them. So in terms of our rocky planets of the inner solar system, first of all, look at Venus. Look how hot it is and how consistent its temperature is. Very little temperature change on the surface of Venus. Venus's surface is above the melting point of lead at all times. Its consistency is caused largely by its thick atmosphere, which insulates the planet. And the surface pressure of Venus is about 100 times the surface pressure of Earth. Then in comparison, look at Mercury. It rotates on its axis 3 times for every 2 times it orbits the sun. So it has a very hot side and a very cold side at all times. And it has no atmosphere to spread the heat around. So lead is melting on the hot side of Mercury, while carbon dioxide is freezing on the cold side, which is really pretty amazing, I think. Notice how much the temperature ranges of Earth and Mars overlap. And then look at the moon. It has a wider temperature range because it has no atmosphere to spread around the heat. And in its permanently shadowed craters, craters where the sun never makes it past the rim, the temperature is marked with a little diamond. The temperature can be as cold as negative 397 degrees Fahrenheit, similar to the temperature on Pluto. So what are the compositions of these atmospheres on Venus, Earth, and Mars that help keep the temperatures more constant? So here's a chart of atmospheres, of atmospheric composition. The atmospheric constituents are down the side, and then in the columns are the values for Earth, Venus, and Mars. The largest chemical constituent is in bold and blue. For the Earth, that's nitrogen. 78% of Earth's atmosphere is made of nitrogen. And for both Venus and Mars, it's carbon dioxide. 95, 96% carbon dioxide, both on Venus and on Mars. The second most common constituent for each planet is in orange. For the Earth, that's famously oxygen. which is entirely the result of having life on this planet. For Venus and Mars, the second most common constituent is nitrogen. On the Earth, the carbon that would be in the atmosphere is bound up as calcium carbonate, CaCO2 carbonate, in limestone rocks in the crust of the Earth. If we liberated all the carbon out of our crust, our atmosphere would be very much like Venus's. And notice another important thing about Venus's atmosphere. Here in this yellow box, it has significant sulfur dioxide and hydrogen dioxide and the toxic reactive hydrofluoric and hydrochloric acids in its atmosphere. It's amazing that any spacecraft has even managed to land and survive for any time on Venus, but more on that later. In fact, I would also note that hydrofluoric acid is famous for dissolving rocks. It's just an incredibly nasty acid. And the fact that it has a little bit in its atmosphere makes Venus incredibly inhospitable. And so finally, let's look at atmospheric pressure now up at the top of the graph. I've just clicked these on. Venus's is almost 100 times higher than the Earth's, and Mars is more than 100 times lower. So they're very, very different in their pressure and in their compositions, although interestingly, Venus and Mars have the same major constituents in their composition. Now let's look at how the planets got their first crusts. This is something I find so interesting, and this is work that I've done with, particularly with Stephanie Brown, who's a postdoc at MIT now. Here's a figure that shows how the earliest crusts form as a function of the size of the body. So it's the radius of the body that we're talking about on the horizontal axis. So starting from the right with the larger bodies, Earths and super Earths, recall from the magma ocean lecture, the idea that all rocky planets went through one or more magma ocean stages, and that those magma oceans froze from the bottom up, and they burped out the earliest atmospheres as they froze. Larger bodies, these larger bodies form their first crusts from volcanism, first from the overturn of their newly solidified mantles in the solid state, just following magma ocean solidification, and then from later interior convection, volcanism goes on. This is likely what happened on Venus, Earth, and Mars. The earliest crusts would be volcanic, but maybe not Mercury, interestingly. Now, recall what happened on the Moon. When solidification of its magma ocean reached about 80%, the mineral anorthite began to crystallize, and anorthite floated in the remaining magma ocean, forming rockbergs, and then finally a continuous lid on the Moon's surface. And that lid is still visible as the bright lunar highlands today. Amazingly, it's quite possible that a similar process happened on Mercury, but instead of anorthite, it was graphite, that black carbon mineral that can be used as pencil lead, that floated. Meanwhile, the smallest bodies, planetesimals, will keep their primitive surface, possibly even if they melt on the inside. Okay, on to the features of these crusts. Now, Mercury, this question of a graphite flotation crust, I just love this. Mercury's surface, it turns out, is markedly darker than predicted from its measured elemental composition. The darkening agent is generally found in large impact craters and in their ejecta. You can see it here colored blue in this image. It suggests that the material that's darkening is in a mid to lower crustal location that gets excavated during impacts. And the only element consistent with both the neutron measurements and the visible to near infrared spectra from the MESSENGER orbiter mission is carbon. And so it's hypothesized that there is a layer of carbon in Mercury's crust that is causing it to be dark. Mercury could have had graphite floating in its magma ocean. So now a few words about how we've learned about and how we try to describe other planets. Early astronomers strained to see the surface of the other planets. Here's a figure from Svante Arrhenius's 1919 book, Planetan, showing a map made by the Italian astronomer Giovanni Schiaparelli. In Schiaparelli's initial observations of Mars in the mid-1800s, he named the, quote, seas and continents of Mars, imagining some things that reminded him of the seas and continents of the Earth, and he called them seas and continents. During Mars's great opposition of 1877, when it was very close and very bright, similar to how it's been this year for us, you can still see Mars outside now at night. It's very bright and very near. Schiaparelli observed a dense network of linear structures on the surface of Mars, which he called canali in Italian, meaning channels, but the term was mistranslated to English as canals. And that mistranslation got Percival Lowell thinking about intelligent life on Mars and led to all kinds of confusions about what could be seen on Mars's surface. This points out how dangerous it is to name features on other planets using the same names we use on Earth. Very often those alien features prove to be nothing like Earth's and have been made through completely different processes. But if we use Earth names for the features on other planets, it implies the same process, and we have to really disentangle it in our minds, like if we name them canals. Planetary scientists today work hard not to imply process when we name features. More on that later. This is also a plate from Svante Arrhenius' book Planeten. I included it just because it's beautiful. This painting of Mars was made by the Greek astronomer Eugene Antoniadi, who came to believe the Martian canals were optical illusions, and in fact, they were. Antoniadi also made the very first ever map of Mercury. And so this is Venus. Early observers thought they might be seeing Venus's surface, and when they looked at it through their telescopes, and they drew maps and they estimated its rotational rate by watching features go by on its surface. But Venus is always covered by thick clouds, so we can only see its surface using radar, or in a few amazing photos taken by the Soviet Venera landers, which braved the incredible surface conditions. In many ways, Venus is the most mysterious of our rocky planets, the one that we know the least about. It's so hard to see. So here we go. Venera 9 landed on Venus in October 22nd, 1975, and it returned the very first image from the surface of another planet. So we have seen Venus's surface. 10 of the Venera missions landed on the surface. Venera 3 in 1966 was the very first human-made craft to enter the atmosphere of another planet. Venera 7 in 1970 was the first craft to make a soft landing on another planet. And the Venera missions 9, 10, 13, and 14 all returned photos from the Venusian surface, still the only missions ever to do so. I think it's really good to dwell on this for a moment and think about it and think how important it is for us to have spacecraft that have visited these places in order to learn about them. Years ago, I was publishing some books on the solar system, and I wanted to publish the very best photograph that we had of every moon and planet in our solar system. And some of them we haven't imaged from up close, and they're just little blurry pixels, but my editor would not allow me to do that. In his mind, every photo had to be sharp, even if no sharp photo existed. Here are some images from Venera 13. Look at those platy rocks. Venera 13 lasted for 127 minutes, the record to this day on Venus. That's how hard it is to get equipment to survive on the surface of Venus. The Soviets even got surface compositions, and some of the rocks are very similar to high potassium continental basalts on the surface of the Earth. I spent a little extra time showing these images because they're not often seen, and we have such an extremely small collection of actual surface photos of Venus. Good to remember that we have not seen everything in the solar system yet. And look at that one on the left. Can't you just imagine you're standing there staring out across the rocky, platy plains of Venus? So amazing. Next, let's compare a kind of feature that occurs on all the rocky planets, which is craters, impact craters. They differ from planet to planet, I think, in a really interesting way. This is a picture of Meteor Crater from Arizona. And it's just what we would expect from a simple crater. It's shaped like a bowl with overturned rock flaps at the edges. So when the bowl is formed, the rocks are flipped over, ejected on the sides, and flipped over on the edges. Craters on other planets do not necessarily look this way. Venus, for example, here's Venus again. Venus has very few craters, partly because impactors don't survive flight through its thick atmosphere, and partly because its surface has been flooded by volcanism and which paved over the older craters. And so this is one of these truths of planetary science, that if there are very few impact craters, it means the surface is surface, old craters have been erased. The high atmospheric pressure and the rapid cooling of the rocks makes the craters shaped a bit differently than on the Earth or on Mars. You can see this crater, it looks different than Meteor Crater. There are 3 impact craters in this image. It's a 3-dimensional perspective view of the surface of Venus. In the foreground is Howe crater, which is about 37 kilometers in diameter. Danilovna is on the upper left, and Aglionice is on the top right. Those are the 3 craters in this picture. With the exception of the Venera photos that we just looked at, Venus surface images are almost all created by radar, as this one is. Radar we can bounce off of Venus and receive back at Earth, and that is how we get these images, and then from some new orbiters, we've done this as well. With the exception, right, so with the exception of just maybe, I don't know, a couple of dozen of surface photos from the Venera landers, they're all radar. So the bright regions are highly radar reflective, meaning that they're rough, and the smooth areas are more radar dark. Radar was also used to make the elevation model used in this image, but the colors come from the photos taken by the Venera landers. Okay, on to Mars. Mars has a lot of interesting craters, and it has one special class of craters called pedestal craters, which is what I wanted to talk about here. If only we could talk about all the things about all the planets, but of course 20 minutes isn't very long. So a pedestal crater is one where the crater and the inner ejecta are above the level of the surrounding plains. Can you see how in both of these pictures the surrounding plains are lower? They're cliffs at the edge of the crater ejecta. Impact events alter the surface by the heat and pressure of the actual impact, and the resultant crater and ejecta are often stronger than the surrounding unaltered surface. And so what happens is the surrounding plains are eroded away, isolating the crater materials to form a platform up above the surface. These craters almost certainly happened in icy regions. The impact went through the ice and lofted more rock into the ejecta blanket, making the ejecta blanket harder to erode than the surrounding icy material. Now, the moon's craters look a bit more like the Earth's, but some of them have a special attribute. The sun never reaches their bottoms, and they can retain ices in their bottoms indefinitely. These are places where people are very actively planning to get ice as a resource from the moon. They're called permanently shadowed craters. And so I'm going to try to show this little video, and I want you to keep your eyes on Shackleton crater right here, which is permanently shadowed, and you can kind of see the other craters out of the corner of your eye while you're watching Shackleton. You can see the shadows go around as the sun goes around, and there's Shackleton staying dark all the time. So it's very, very cold down there. Remember, as cold as Pluto. And so that is a place where we're going to look for ice as a resource. All right. Now, a few minutes ago, I talked about how we now try not to name features on other planets such that we're implying their process. Here's a great aerial view of the San Andreas Fault in California. It would have been tempting to think of this as a canal, wouldn't it be, if you were looking at it without a knowledgeable eye? But instead, it's a feature of plate tectonics. Earth is the only planet known that has plate tectonics, and plate tectonics may be a key for the development of advanced life forms. We're going to talk about that more in the next lecture and the final lecture. So let's look at some strange and unique features on other planets besides the Earth. Channels on Venus. Can you see the dark? I'm gonna run my cursor along it. Do you see this dark channel that goes across this picture? This is a radar mosaic that shows an area on Venus with dimensions of about 130 by 90 kilometers. And there's a 200 kilometer long segment of a sinuous channel. This channel is about 2 kilometers, just over a mile wide. And these channel-like features are common on the plains of Venus. Another Venusian channel, not this one, a different one, is more than 7,000 kilometers, 4,200 miles long, longer than the Nile River, which is Earth's longest river, thus making that Venusian channel the longest known channel in the solar system. Both ends of its channel are obscured, so maybe the original length was even longer. In some places, they appear to have formed by lava, which may have melted or thermally eroded a path like a river. They resemble Earth's rivers in some respects, with meanders in them and what are called cutoffs, where the river leaps across a tight bow, and abandoned channel segments. But the Venusian channels are not as tightly sinuous as Earth's rivers. That the Venusian channels was more viscous than water, but not as thick as terrestrial lava. So one of the best hypotheses is that these channels were carved by liquid carbonate rock. This is known as carbonatite lava. There's only one place on Earth right now where carbonatite lava is erupting, and that is the Oldonyo Lengai volcano in Tanzania. Go look at videos, it is amazing. But on Venus, these carbonatite channels may mark the moment when carbon, previously locked in rocks as it is on Earth, melted, flowed, and evaporated into the air, creating the dense carbon dioxide atmosphere Venus has today. Think of that. I love these channels. Here's a linear feature on the moon. These are referred to as rills since they were named before their identity was understood, so they were given a kind of a anonymous sounding name. It turns out they're collapsed lava tubes. Lava used to flow through them from its eruption site to a distant place where the lava could pour out. After the last lava drained, the tubes sometimes collapsed. And finally, here's Mars. Here's an exotic looking landscape. This is part of the Martian South Pole. Both the North and the South polar caps on Mars are mainly made of water ice, but both get thick coatings of carbon dioxide, that is dry ice, in the winter. The circular pits are holes in the dry ice layer that expand by a few meters each Martian year. In the winter, new carbon dioxide ice is added to the cap by freezing directly from the atmosphere or falling as snow, carbon dioxide snow. Pulling the carbon dioxide from the atmosphere into the ice cap causes Martian atmosphere to fall by 30% from its already low 0.6% of Earth's atmospheric pressure. This atmospheric fall occurs in both the southern winter and the northern winter. So the pressure of the atmosphere on Mars is constantly oscillating back and forth. Now, one last thought about rocky planets in other solar systems. The Kepler mission's formal goal was to measure a number that's called eta Earth. That is the fraction of sun-like stars that have an Earth-sized object orbiting them in the habitable zone. So how many sun-like stars have Earth-like planets that are in the habitable zone, where it's warm enough for the surface to retain liquid water? The team has done a new calculation, just came out very recently, and they calculate that at least a third and maybe as many as 90% of the stars similar in mass and brightness to our sun have planets like Earth in their habitable zones. We think that there are at least 100 billion stars in the Milky Way, maybe 4 times that many, but 100 billion we're going to take as a minimum, of which about 4 billion are sun-like. If half of them have habitable planets, then there are 2 billion rocky Earth-like habitable planets in our galaxy, just in the Milky Way. So on average, the astronomers calculated the nearest such planet would be about 20 light years away, and there should be 4 of them within 30 light years or so of the sun, which is kind of amazing. I just feel like we cannot be alone. So finally, that is a lightning comparison of the inner solar system. Mercury has an extreme temperature range, no atmosphere, possible graphite flotation crust. Venus is hot, hot, hot all the time, thick carbon dioxide atmosphere, possible carbonatite rivers in the past. Earth's average temperature is just above water freezing. It has this unique nitrogen and oxygen atmosphere and unique plate tectonics. And Mars, from a pleasant 70 degrees Fahrenheit down to negative 200 with a thin carbon dioxide atmosphere that fluctuates by 30%. It's a lightning comparison of the inner solar system's rocky planets. And next time I'll talk about plate tectonics and atmospheres. Thank you so much for coming. I really appreciate it.